This scene deals with the subject many fathers find so difficult.
Welcome to Podcast V0.1, where we break down the latest research and tools for curious engineers. Today, we're diving into a fascinating paper titled Comparison of Static Analysis Architecture Recovery Tools for Microservice Applications. Now, if you're relying on static analysis to understand your microservice architecture, you'll definitely want to hear this. A new study benchmarks existing tools and finds not only which ones perform best, but that combining them can significantly boost accuracy. The F1 score, a measure of a test's accuracy, jumped from a decent 0.86 for the top single tool to an impressive 0.91 when tools were combined. That's a pretty significant leap, and we're going to explore how they got there. So, let's set the stage. Microservice architectures are everywhere, offering benefits like scalability and independent deployment. But they also present challenges, particularly in understanding the overall system. With many services interacting, keeping track of connections can be daunting. This is where architecture recovery tools come in, promising to automatically map your system. This overview is crucial for development, maintenance, and especially for smooth integration into CI/CD pipelines. That's continuous integration and continuous delivery, allowing teams to catch architectural issues early. However, there's been a gap. While many tools for microservice architecture recovery exist, a comprehensive comparison of their real-world accuracy has been lacking. This paper, by Simon Schneider and a team of researchers, addresses exactly that. They identify static analysis tools, benchmark them rigorously, and uncover that combining their outputs yields the best results. The researchers focused on static analysis tools. As you likely know, static analysis examines code without running it. This makes these tools lightweight and fast, ideal for CI/CD pipelines, where you need quick feedback without the overhead of dynamic analysis, which requires running the system. To find these tools, they conducted a multi-vocal literature review. This means they cast a wide net, searching not only academic databases like Scopus and IEEE Xplore, but also gray literature sources such as X, Reddit, and Medium. This broad search is smart, as many useful developer tools emerge from community discussions. They initially identified 13 tools that fit their criteria: static analysis for microservice architecture recovery, and being freely available. Here's an interesting point that many engineers can relate to when trying new tools, especially academic ones. Out of those 13 freely available tools, the researchers could only successfully execute and benchmark 9. Nearly a third couldn't be run for the study due to issues like missing dependencies or unclear instructions. This highlights challenges in the reproducibility and usability of research tools and is a crucial point for practitioners evaluating new software. For the 9 tools they could run, the team used a common data set of 17 open-source Java Spring microservice applications. The paper notes that Java is reported as a very popular language for microservices, and Spring is a widely used framework for them, making this data set highly relevant. They measured accuracy using precision, recall, and the F1 score, which balances the two. The evaluation focused on detecting architectural components, like services and databases, and the connections between them. The paper notes that detecting components is often easier, thanks to deployment descriptors like Docker Compose or Kubernetes files. Detecting connections, however, is more complex due to the diverse communication mechanisms microservices use, such as direct API calls or asynchronous messaging. The study also looked at additionally extracted characteristics. For their comparative benchmark, the main additional characteristic evaluated was the detection of API endpoints, specifically RESTful HTTP endpoints indicated by common Java annotations, like @request mapping. The researchers even extended their dataset's ground truth for endpoints, manually identifying 63 additional ones to ensure a fair comparison. So what were the big results? The best performing individual tool achieved an overall F1 score of 0.86. That's quite good. But the standout finding was the improvement from combining tool outputs. By strategically merging the results from a specific combination of 4 tools, they achieved an F1 score of 0.91. This suggests a powerful synergy, where different tools, each with unique strengths, collectively create a more complete architectural picture. This finding about tool combination is the core takeaway. The paper details that tool outputs were combined using logical operators. For example, a characteristic might be considered detected if any tool in a combination found it, an OR approach, or only if all tools agreed, an AND approach. The combination of 4 tools that achieved the 0.91 F1 score was selected because it maximized the overall accuracy metrics. Now you might be thinking about the practicalities of setting up and merging results from multiple static analysis tools in a real-world CI/CD pipeline. The paper focuses on demonstrating the potential benefit rather than providing a turnkey solution. There would be overhead in managing multiple tools and merging their outputs. However, the significant accuracy boosts suggest that for critical systems, such an approach could be worthwhile. Another consideration is how these findings translate to systems built with different languages or frameworks. The benchmark used Java Spring applications. While the paper doesn't directly address other tech stacks, the principle that different tools have different strengths likely holds true more broadly. This study provides a strong data point for Java Spring and a compelling hypothesis for other environments. Revisiting tool usability. The difficulty in running nearly a third of the identified tools is a sobering reminder. It underscores the importance of well-maintained documentation and robust implementations, especially for research tools aiming for practical adoption. Regarding those additionally extracted characteristics, while tools might claim to find various details like security mechanisms, endpoints was the primary one for which a comparative benchmark was feasible across multiple tools in the study. The impressive 0.91 F1 score for the combined approach was mainly for the core architecture, components and connections. So what's the big so what? For us software engineers? This paper offers data-backed insights. First, it provides a benchmark for static analysis tools for Java Spring Microservices. Second, it highlights the power of ensemble methods. Just as in machine learning, combining specialized static analysis tools can lead to a more accurate understanding of complex systems. The challenge shifts from finding one perfect tool to finding the optimal combination and orchestration strategy. The paper also stands out for its methodology, employing a multivocal literature review and being based on a registered report. This means its research plan was peer-reviewed before the main study, adding rigor and transparency to the findings. In conclusion, this research suggests that if you're serious about understanding your microservice architecture via static analysis, consider a combined approach. While individual tools offer good insights, thoughtfully combining their strengths can lead to significantly more reliable architectural recovery. The jump from an F1 score of 0.86 to 0.91 represents a much clearer map of your system, which is invaluable in the complex world of microservices. It's a call for practitioners to explore tool combinations and for tool builders to consider interoperability. That's all for this episode of Podcast V0.1, and remember to stay curious.